Hi, this is my third lecture in the topic vector integration, which comes under Unit 5 of your syllabus. In this unit, already we covered how to find out the line integral and how to find out the work done in moving a particle along a curve and how to find out the conservative function and surface integral in these previous two lectures. In this lecture, we are going to learn an important theorem in vector calculus, that is Green's theorem in a plane. So this theorem is confined to a plane, a two-dimensional one, and also some examples on Green's theorem. This we are going to learn in this lecture. So let us see the statement of this Green's theorem. In your syllabus, in vector calculus, you have three theorems. One is Green's theorem, Stokes' theorem, and Gauss divergence theorem. For all these three theorems, the proof is not is beyond the scope of the syllabus. Therefore, I am not going to deal with the proof of this theorem, but the statement and what actually the statement says. That discussion will take it now. Okay, this is the statement of the Green's theorem. So if you have a function of two variables, f of xy, and another function of the same variables xy, f and g are two functions of two variables xy, and this f with respect to y, this g with respect to x, and these four are continuous in a region E of the xy plane, because the Green's theorem in a plane we are dealing with in a region E of the xy plane, and that region E is bounded by a closed curve C. So this is the closed curve C, and this is the region E. Then in the previous two lectures, I learned how to find out the line integral of a vector point function. And in the third unit, we learned double integration of double integration over a region E. Those two we learned. That this theorem combines those two. If f, g, dou f by dou y, dou z by dou x are continuous in a region E and bounded by a closed curve region E of the xy plane bounded by a closed curve C, then the integral over C f dx plus g dy, f dx plus g dy is the line integral, is equal to double integral over E dou z by dou x minus dou f by dou y dx dy. This is the statement of the Green's theorem, or we can say the statement in this way. Suppose you have a vector point function in defined on the xy plane. F bar is capital F bar is fi bar plus g j bar. As I mentioned in the previous two lectures, some people will pronounce this as I crown. Some people will use this j crown and I crown, but I am habituated to read it as I bar and j bar. Anyway, they are the unit vector. Take it in that way. F bar is fi bar plus gj bar, and if you have a, and you know that f and g are the this is x component of capital F bar, this g is y component of F bar. So the x component with respect to y component with respect to x are and f g, they are continuous in a region E of the xy plane bounded by the closed curve C. Then the line integral of capital F bar is equal to double integral over E dou z by dou x minus dou f by dou y. This is the difference of the derivatives of y component with respect to x and x component with respect to y, dx dy. So this Green's theorem converts a line integral to a double integral. Green's theorem converts a line integral to a double integral. I think you have understood very clearly the Green's theorem. For applying Green's theorem, we should have one region or one closed curve. That is, this is more important. You need to have one closed curve. Whenever you have a closed curve, automatically that closed curve will be the boundary for some region E. Now, because you have one closed curve, you can find out the line integral of some vector point function f bar along C. You can find out the line integral. What line integral is, we learned in the previous lectures. So line integral of f bar along C we can find out. Whenever you have a line integral of f bar along C, now from f bar, because f bar is a vector point function, it will have the x component, y component. Find the difference of the partial derivatives of x component with respect to my y component with respect to x and x component with respect to y, that is dou z by dou x minus dou f by dou y. Now that difference you have, this is equal, that line integral is equal to double integral over e dou z by dou x minus dou f by dou y dx dy. You need to understand the relation between the c and e. Relation between c and e is c is the boundary for e. What is the integrand for the line integral? It is f bar. And what is the integrand for the double integral? It is dou z by dou x minus dou f by dou y. This is what Green's theorem is. Now, as an application of Green's theorem, let us learn one important result. So in Green's theorem, in place of f if I take minus y and in place of g if I take x, that means I am considering a function f bar which is minus y I bar plus x j bar. This is the function what I am considering. If I apply Green's theorem on it, just now we learned what Green's theorem is. The line integral of f bar. What is line integral of f bar? F bar dot dr bar. That is f dx plus y dy. So f dx plus y g dy. This is the line integral of this f bar is equal to what the Green's theorem says. It is equal to double integral of dou z by dou x minus dou f by dou y. This is g. Y component is g. Derivative with respect to x. This is 1 minus the x component is minus y. The derivative with respect to y is minus 1. Difference of these two is 2. So double integral over e 2 dx dy. Therefore, what we have is integral over c minus y dx plus x dy is equal to twice double integral over e dx dy. You learned double integral over e dx dy gives the area of the region E in the third unit of your syllabus. Therefore, if I combine these two, then I can understand that area of a region E is equal to half of integral over c minus y dx plus x dy. This is mathematically what you have. If I convert that into verbal form, so area of a region E, how do you get the area of a region E? Area of a region E is half of the line integral of what function? Minus yi bar plus xj bar. Area of a region is always equal to the half of the, don't forget this half of the line integral of minus yi bar plus xj bar along the boundary curve C of E, because you are finding the area of a region E. For that region, see the boundary curve. Along that curve, find the line integral. Line integral for what function? For minus yi bar plus xj bar. For this function, if you find the line integral, you will get the area of the region. This is one important result what we can deduce from Green's theorem. Okay. Let us solve these 6 examples related to this Green's theorem. The first one is verify Green's theorem for f bar is equal to 3x minus 8y square I bar plus 4y minus 6xy j bar. For that function, you need to verify the Green's theorem, and C he has given is the region bounded by x0, y0 and x plus y is equal to 1. So that is the first problem. So you have to verify this. In this, what Green's theorem says, it converts a line integral to their double integral. So line integral is integral c f dx plus g dy is equal to, or else you can call it as f bar dot dr bar. Both are same. F bar is 3x minus 8y square I bar plus 4y minus 6xy j bar is equal to double integral over e dou z by dou x minus dou f by dou y dx dy. This is what we know from the Green's theorem. This we have to verify. Verify in the sense you have to find out the left hand side and right hand side and see whether those two are equal. Now we need to understand what this E and C. That he has given. C is the boundary. So you have here the boundary. What is that boundary? Bounded by x is equal to 0. X is equal to 0 is y-axis. Y is equal to 0, that is x-axis. And the line x plus y is equal to 1. So this is your region E, and this is all your boundary. What is your boundary? The line OA, and next the line AB, and the next line BO. OA, AB, BO, this is your boundary, and this is your region E. So this is your region E, and this is the boundary. What Green's theorem says? The line integral along this boundary is equal to double integral over this region E. For finding the line integral, the integral is your f bar, and for finding the double integral over E, your integrand is dou z by dou x minus dou f by dou y. Okay. Now, what is your f? This is always f, as I said, f is the x component, that is the dx coefficient. Sometimes in the examination, he may give here g dy plus f dx, he may write. Observe what actually he has written. F is 3x minus 8y square, and g is 4y minus 6xy. F dx, this is f, this is g. This is y component. Derivative of y component with respect to x, that is derivative of g with respect to x is minus 6y. Derivative of the x component with respect to y, that is dou f by dou y, is minus 16y. The difference of these two is 10y. So what Green's theorem says? The line integral of this is equal to double integral over e 10y dx dy. We need to find the right hand side as well as the left hand side. Let us find out the right hand side and left hand side. So first I am finding the right hand side. I am finding the double integral over e 10y dx dy. You learned how to find out the double integral in the unit 3. So this in this region E, what are the limits for y? What are the limits for x? If I for a given, if y is given to you in this, for a given y, the lower value for x is 0, the maximum value for x is 1 minus y. Therefore, if a given y varies from 0 to 1 minus y. So this is integral 0 to 1 minus y, and where that y varies from y is equal to 0 to y is equal to 1, because this point is 0, 1. This is the line y is equal to 1. So y varies from 0 to 1, 10y, and because these are the functions of y, these are the limits for x, therefore I need to do the integration with respect to x first, next y. So if I integrate it, this is 0 to 1, 10, y is constant because I am doing the integration with respect to x. Integral for 10y is 10y into x. In place of x, I need to substitute the limits. Those limits are 1 minus y dy. If I integrate, 10 comes out. Y integral y is y square by 2 minus y square is there. Y cube by 3 is the integral between 0 to 1. If I integrate this, this is 10 times 1 by 2 minus 1 by 3. This is 1 by 6. This is 10 by 6. 10 by 6 is 2 5s, 2 3s. So this is 5 by 3 is the value of this line integral. What I got on the right hand side, 5 by 3. I have to get this left side also 5 by 3. Then the theorem is correct. So I will now find out the left hand side. What is left hand side? Left hand side is finding the line integral. Here I am drawing that figure once again. So this is OAB. OAB is the curve. OA, AB, BO is the curve. So the curve C is union of line segments. This is OA and AB and BO. Therefore, this line integral is f dx along OA, along AB, along BO. Those three I need to find out. I'll call it as 1. So first of all, I'll find out the line integral along OA. Along OA, this is OA, its equation is y is 0. So y is 0, and when y is 0, dy is also 0, and x varies from 0 to 1. X varies from 0 to 1. This is along the boundary. Don't consider this inside region, only the line integral we are finding. That means only the curve we have to take. X varies from 0 to 1. Now, what is integral along OA? This f dx plus g dy. this value is integral 0 to 1, x varies from 0 to 1. Along OA, dy is 0, therefore this is 0, and only this value will have. In this, y also 0, so ultimately 3x, y is 0, 8y will be 0, 3x dx. If I integrate, x square by 2 is the integral, and if I substitute the limits, I will get 1 by 2, 3 by 2. So this is 2. Let us find out the next one. Along after OA, AB, along AB. What is AB? AB is my y is equal to 1 minus x. Therefore, what is your dy? dy is minus dx. dy is minus dx. And I am moving from A to B, OA, AB in this direction. So here the value of x is 1 and the value of x here is 0. So x I am converting in terms of x. As I mentioned at the in my lecture 1 of this unit, at the line while finding the line integral, I said while finding the line integral, the entire integrand integral f bar dot dr bar, this entire one is to be converted to a single variable. Whatever you do, may take parametric form or may or convert in terms of x alone or y alone based on the curve, equation of the curve. Here is the equation of the curve. This from this curve I can replace wherever I have y, I can replace with 1 minus x, which will be in terms of x, and dy we can replace with dx. X varies from 1 to 0. Therefore, along AB, what is my integral along AB, my f dx plus g dy is integral 1 to 0. So you know what your f is. Your f is this. In this, I need to write in place of y 1 minus x. So I will write here f value is 3x minus 8 into y is 1 minus x whole square. This is 3x minus 8 minus 8x square plus 16x. That is my f in terms of x. Similarly, what is our g? G is 4y, that is y 4 minus 4x minus 6x into y, y is 1 minus x. If I simplify it, it is 4 minus 4x minus 6x minus of minus plus 6x square. This is my f, this is my g. f dx and dy is my dy, here it is minus dx. Therefore, in place of dy, I need to write minus dx. So this g dy will be this entire thing multiplied with minus g dx. So these two are to be added. This is my f dx. So if I find f dx plus g dy, let us see what is your end result. So if I add these two, g dy is, this is minus dx, one minus sign is there. So here you have minus 8x square and minus 6x square. That will be minus 8x square minus 14x square. So I will write minus 14x square. After that, x term. What is the x term? X term here I have 3x plus 16 plus 3, 19. 19 minus of minus plus 19 plus 4, that is 23. 23 plus 6, 29. So total 29x is there. Let us see the constant also. Here I have minus 8. This is minus 4, minus 12. So this 29x minus 12 dx. Now integrate. I'll move multiply with minus so that I can have 0 to 1 as the limits. So it is 14 x cubed by 3 minus 29 x square by 2 plus 12x after substituting the limits. So if I simplify this, I'll get 6 as the LCM. So this is 28, 329s, that is uh, 87, 6, 7, this is plus 612, 72 minus 87. So 72 minus 87 is minus 15. 28 minus 15 is 13, 13 by 6. So along AB it is 13 by 6, call it as 3. And along BO, along BO equation is x is equal to 0 and along BO x is 0 and dx will be 0. Dx is also 0. So therefore, integral over BO f dx plus g dy will be equal to, and whenever this x is becoming 0 here, this y varies from 1 to 0. Y will be 1 here, y will be 0 here. Integral 1 to 0, this is 4y dy. Dx first term will be 0 and second part 4y 0. So if I change the sign, I'll get minus 4 y square by 2, so that it will be minus 2. So I have along OA, along AB, along BO, all the three we found. Therefore, integral over C f dx plus g dy is equal to along AB I got here 3 by 2. Along AB I got 13 by 6 and along BO I got minus 2. If I simplify these to 6 is LCM, 2 goes 3 times, this is 9 plus 13 minus 12. This will be 10 by 6, which is equal to 5 by 3. Left side also I got 5 by 3. Right side already I evaluated for double integral, that is 5 by 3. So left side and right side I am getting the same value. Thus Green's theorem is verified. Now this ends with the first problem. Let us see the second one. Verify Green's theorem. Again, here also we need to verify Green's theorem for this. That is, this is f bar is this, f is this, g is this. This f dx plus g dy. C is the rectangle with this. Unlike the previous one, here the uh, curve is a rectangle. This is x-axis and this is 0, 0. This is pi 0. This is pi comma 1. This is 0 comma 1. So this is x-axis, this is y-axis. This is my region E. What is my curve? Curve is, if I call it as O, A, B, C, OA, AB, BC, CO. That is my closed curve. Whenever I have, as I said, for the application of Green's theorem, we should have a closed curve. If you have closed curve, automatically there will be a region E for which that C is the boundary. And the line integral along C is equal to the double integral along E. So this is what Green's theorem says. Here f is x square minus cos hy. G is Here x is, see, just now I mentioned. Here he has given some f dy plus g dx. So instead of remembering it as f and g, you just x component, y component. X component is quotient of x component is this. That is my f, x square minus cos hy. This is g, y plus sin x. Don't always write whatever first is given, that is f. So derivative of x component with respect to y, derivative of x square minus cos hy with respect to y is this is f, dou f by dou y. Derivative of cos hy is sin hy, so minus sin hy. And dou g by dou x is with, if I differentiate with respect to x, derivative of sin x is cos x. Difference of these two is cos x plus sin hy. Hence, we need to show that verification means we need to show that these two are equal. Cos hy sin hx plus this. This verification we need to do. So in this region, if I want to evaluate the right side, double integral over E. So what are the limits for y and x? Y limits are, this is y is equal to 0, this is y is equal to 1. Y limits are 0 to 1, x limits are 0 to pi. 0 to pi. Cos x plus sin hy dy dx, because I have written the y integral first. So therefore 0 to pi, I am doing the integration with respect to y. Integral for cos x is cos x into y, and integral y limits, if substitute the y limits, I'll get 1 plus derivative sin hy. Integral for sin hy is cos hy, and if I substitute the limits, it is cos h1 minus cos h0, cos h1 minus cos h0. This is the integral for sin hy dx. Now, integral cos x is sin x. If I substitute the limit 0 and pi, I'll get sin 0 and that will be 0, plus this is some constant. What is that constant? Cos h1 minus cos h0 into x. If I substitute the limits, that is pi. So ultimately what I get is pi times cos h1, it is e plus e power minus 1 by 2, cos h1 e power x plus e power minus x by 2, cos h0 is 1. So this is what we have uh, for this double integral. So this is my right hand side value. I need to find out the right hand side, left side also. I need to find out the left line integral over C. What this line integral? C is my closed curve. This is union of four line segments OA, AB, BC and CO. Let us find out the line integral one by one. So remember, this is y side y x square minus cos hy and y dx. So first one is along OA I am finding out. So along OA, the OA is x-axis, that is y is 0 and dy will be 0. Therefore, dy is 0, that goes out, and x varies from 0 to pi. If you remember, this is the curve. This is y equal to 0, this is x is equal to 0, this is x is equal to pi, and this is y is equal to 1. Along this, here to here, x varies from 0 to pi, dy is 0, and y is 0, cos h0 is 1, x square minus 1 dx. Integral x square is x cube by 3. If I substitute the limits, it is pi cube by 3 minus x, that will be minus pi. So this is 1. Next, along AB, I will find out. AB, from here to here. From here to here, y varies from 0 to 1. And its equation is, along AB, x value is pi. Then dx is 0. Y varies from 0 to 1. Dx is 0, therefore I don't need to consider this. In this, x is pi, y is there. Pi, if I substitute sin pi is 0, y dy. If I integrate, that will be 1 by 2. So this is my third one. This is my second one. I'll call it as 1. Everything I'll substitute in the first. And the next is along AB and now BC. This is my BC. Along BC, what is the value of y? Y is 1, dy is 0. Y is 1, dy is 0 means this value will go out, and y is 1, x square minus cos h1 dx. What are the limits for x? X limits are from pi to 0. Here, the direction is also more important. Always don't write 0 to pi. From here to here, it is moving. Therefore, pi to 0 are the limits. So if I go to the next one, it is limits are pi to 0, and dy has become 0, dy is 0, and dx is x square minus cos h1 dx. X square minus cos h1 to dx. If I take minus common, or if I interchange the limits, it will be cos h1 will come first, cos h1 into x. If I apply the limits, it is pi minus x square, integral x square is x cube by 3 If I shoot the limits, is minus pi by 3. And the last one is OA is completed, AB is completed, BC is completed, and now along CO. CO is this. This is C, this is O, this is 0, 1, and this is 0, 0. And here you have x is 0. Along CO, x is 0, therefore dx is 0. Only y varies from 1 to 0. Y varies from 1 to 0. Let us see the integrand. Here along this dx is 0, so this goes out, and here x is 0, sine 0 is 0, and only y will be there. Y dy, y varies from 1 to 0, 1 to 0, y dy. If I interchange the limit 0 to 1, so that I'll have minus y square by 2, minus 1 by 2. So this is the fifth one, and this is fourth one. And here, therefore, from substituting 2, 3, 4, and 5 in 1, what is that we'll get is integral over C f dx plus g dy will be equal to 1 is, what is your, the second one, pi cube by 3 minus pi, it is 1 by 2, pi cube by 3 plus 1 by 2, and here it is minus pi cube by 3, and here cos h1 into pi. I think what is pi cube by 3 minus pi. Pi cube by 3, yeah, this is minus pi. Pi cube by 3 minus pi, and this is cos h1 into minus pi by 3, and this is minus half. Cos h1 pi minus half, and plus half is also there. There is plus half. Yeah, this is my plus half. So if I simplify this, plus half minus pi cube by 3, for these two, if I take pi common, it is cos h1 minus 1. This is pi times cos h1 is e plus e power minus 1 by 2 minus 1. This is what I got for RHS also. So LHS and RHS are same. Therefore, the line integral and the double integral are same. That means the Green's theorem is verified. Now, the theorem what we learned, Green's theorem, from these two examples, you can understand that the Green's theorem is verified and it is correct. The actual mathematical proof is not there in the syllabus. That is why I have not given that. Now coming to the next problem, find the area of the ellipse whose semi-major and semi-minor axes are A and B by evaluating a line integral. By finding the line integral, find the area. For finding the area in third unit, you'll learn how to find the area of a region by double integral dx dy. That already you learned there. Don't use that, but you by evaluating a line integral find the area. That conversion this Green's theorem gives. So here you have a ellipse whose semi-major axis is A, minor axis is B. Therefore, it is equation is x square by a square plus y square by b square is equal to 1. This is my region E. This is my C. So I'll start from here. It is A, B. This is A dash, B dash. So my curve is AB, A, B, A dash, B dash, A, closed. So just to make it closed, wherever I started, I have come back. So that for that region is E. So what Green's theorem says, as application from Green's theorem, we know that already at the beginning I have given you that idea. Area of the region, area of any region is half of the line integral of this. This function you need to remember. Line integral of this along the boundary of the region. So therefore, for finding the area of this elliptic region is half of the line integral of this along the boundary. What is the line integral of f bar along the boundary? It is f bar dot dr bar. F bar dr bar is line integral is this. This I think you know integral over C. Line integral is f bar dot dr bar. F bar is this. What is dr bar? Dx bar dxi bar plus dy z bar. What is the dot product of these two? F dx plus y dy. F is minus y. This I have to evaluate for finding the area along this curve. Therefore, area of the lesion is half of this I have to evaluate. Integral over c minus y dx plus x dy. How to find out this? So, as I said, for finding the line integral, our aim is to always reduce this to a single variable. I use the parametric representation of an ellipse. You know that x is, so along C, what is that you know? Along C, C means along the boundary, this is my C. This is ellipse. This is elliptic region. Along C, my x is a cos theta, y is b sin theta. When x is a cos theta, my dx is minus a sin theta. dy is b cos theta. So this is my area is half of, whenever I take this, theta varies from 0 to 2 pi. 0 to 2 pi minus y means minus b sin theta into dx. Dx is minus a cos theta, therefore it becomes plus a will be there, ab, again sin theta, sin square theta, plus x is a cos theta, a cos theta into dy is b cos theta. So if I take AB common, AB by 2, integral 0 to 2 pi, sin square theta plus cos square theta, dx is a sin theta, d theta also will be there. Cos square theta plus sin square theta is 1, so this is d theta. So AB by 2 into 2 pi, that will be pi AB. Pi AB is the area of the ellipse. This is how we solve this problem. Coming to the next one, find the area between the parabola y square is equal to 4x and x square is equal to 4y with the help of the Green's theorem in a plane by evaluating a line integral. Here also we need to find out the line integral. So what is the boundary? What is the C here? We need to find out. The C is this is one parabola, x square is equal to y, and this is another parabola which is y square is equal to x. Now find the area between the parabolas. This area I want. This area, if I call it as E, is equal to half of the line integral of this along this C. Now what is your C? This is O, A, B, C, O. Now the curve is O, A, B, B, C, O. That is the curve. So C is arc OAB union arc BCO. So along the C is sum of those two. Therefore, area is half of integral along the arc OAB minus y dx plus x dy plus half of along the arc BCO minus y dx plus x dy. So this is half of half of along OAB. What is this equation? Y is equal to x square. Along this OAB, I have y is equal to x square. Then what is your dy? dy is 2x dx. So everything I am converting in terms of x. X varies from 0 to, what is the point of intersection here? Y square is equal to 4x and x square is equal to 4y. These are the curves what he has. So the integral, the point is 4 comma 4. So 0 to 4 are the limits for x. 0 to 4 minus y. What is minus y? That is minus x square dx. The dx I am keeping as this plus x dy. What is your dy? dy is 2x dx. 2, so 2x square dx. So here minus y is x square by 4. Here the equation is 4y is equal to x square. Then y is x square by 4. So minus y is minus x square by 4 plus x into what is your dy? 4y is equal to x square. Dy is equal to 2x dx by 4. So 2x square by 4. Ultimately, if I simplify this, what is that I'll get? Half of integral 0 to 4 2x square minus x square, that is x square by 4 dx. Similarly here, half of, let us see here, along BCO, 4x is y square. That means x is y square by 4. I am converting here, x is y square by 4. Then dx is 2y dy by 4. So I will convert everything in terms of y here. So that it is minus y I am keeping as this. Dx is, what is my dx? Dx is 2y dy. So 2y dy by 4 plus x is y square by 4 dy. The dy I am keeping as. So this is plus half of, and now here the limits for y. From here to here, the y limits are from 4 to 0. If I make it 0 to 4, minus 2y square by 4 plus y square by 4 is minus y square by 4 because I changed the limits. This becomes y square by 4. If I integrate, half I can take common into 1 by 2 into, that is 1 by 8, 4 into 2, here also 4 into x square integral is x cube by 3. X cube is 4 cube, 64 by 3 plus here also another 64 by 3, and if I simplify it, 8 goes the 2 times 64 by 3, this will be 16 by 3. So area between the two parabolas is 16 by 3. So this gives the uh, application of that Green's theorem. Coming to the next problem, using Green's theorem in a plane, eval where C is the square formula. Find out this line integral. He is asking us to find out the evaluate line integral. Instead of, you can find, because he is asking us to use Green's theorem, you have to apply Green's theorem. If he doesn't mention this part, if he doesn't mention this part, then simply if he gives this problem evaluate, then choice is yours. You can find out the line integral by the methods what already I have given you in the lecture 1. Because he mentioned here Green's theorem, definitely you have to convert this line integral to a double integration and do it. So this is what he, by Green's theorem, we know this one. He has given dx quotient is x square into 1 plus y. This is, so dou f, dou g by dou x is this, dou f by dou y is this. If I find the difference between these two, this is what I get. Hence integral, or see, this integral is the Green's theorem says this line integral value is simply equal to this double integral value. Where what is this e? E is the region bounded by x is equal to plus or minus 1, y is equal to plus or minus 1. So this is x is minus 1, this is x is 1, this is y is minus 1, sorry, this is x is equal to minus 1, this is x is equal to 1, y is minus 1, y is plus 1. This is origin, this is x-axis, and this is y-axis. Now in this is my region E. In this region, I need to find out the double integral. So what is the 2 comes out? What are the limits for y? Y limits are minus 1 to 1. X limits are also minus 1 to 1. X square dx dy. So it is, because it's an even function, it is 2 times, so 4 times. Integral x square is x cube by 3. So 1 by 3 into integral minus 1 to 1 dy, this is 2. So ultimately it is 8 by 3. Integral dy is y. If I substitute the limits, that will be 2. 2 into 4, 4 into 1 by 3, that is 8 by 3. So the line integral value is 8 by 3. See how simple to evaluate a line integral if you use the Green's theorem. But don't be in the impression that every line integral can be converted to a double integration. Only when the line integral along a closed curve. So because it is closed curve, I am able to find out this line integral instead of doing that laborious one. Simply by finding the double integral, the value what I get is equal to the line integral value. So this is, if coming to the other problem, evaluate again, he is also asking to evaluate the line integral of this curve, uh, where C is this curve. So Green's theorem, the line integral value is equal to the double integral. Here F is the I bar coefficient, it is minus x square y. Y is G is J bar coefficient, it is plus xy square. Dou Z by dou x is y square. Dou F by dou y is minus x square. If I subtract one from the other, this is what I get. Therefore, line integral is equal to double integral over E dou z by dou x minus dou f by dou y dx dy. This what I have to find out, where E is the region bounded by this. What is R is equal to A into 1 plus cos theta? All of you know at the, I mentioned at the time of multiple integrals. So this is the region E, and R is equal to A into 1 plus cos theta. It is given in the polar coordinates. So this is double integral. So here, this is in polar coordinates. I am converting that to polar coordinates. What are polar coordinate conversion? X is r cos theta, y is r sin theta. In polar coordinates, what is dx dy is r dr d theta. This we learned. So x square plus y square is r square, dx dy is r dr d theta. And what are the limits for r and theta? For finding the limits r, I need to take from 0 to this. So r value 0 to a into 1 plus cos theta, and theta varies from 0 to pi. Here again from pi it goes to 2 pi, from 0 to 2 pi. So this is integral 0 to 2 pi. Integral r cube is here. Integral r cube is r power 4 by 4. If I substitute the limits, a power 4 into 1 plus cos theta whole power 4 by 4 d theta. So if I find it, this is a power 4 by 4 integral 0 to 2 pi 1 plus cos theta whole to the power of 4 d theta. Now a power 4 by 4, if I integrate, this is 0 to 2 pi integral, this is 1 a plus b whole power 4, apply the binomial expansion, 4c1 into cos theta, 4c2 into cos square theta, 4c3 into cos cube theta, 4c4 into cos power 4 theta d theta. Even from the intermediate level itself, you know that integral 0 to 2 pi sin theta power n into cos theta power m d theta is equal to 4 times integral 0 to pi by 2 only when m and n are even, otherwise 0. If we have both or if you are same. So because m here, everything in terms of cos, whenever you have odd power for cos, that will be 0. You can easily under integral cos is sin theta. If I substitute the limit 0 and 2 pi, that will be 0. So this and this goes out, remaining part will be there. So a power 4 by 4, 4 times 0 to pi by 2. Whenever it is 0 to pi by 2, integral for 1 is theta. If I substitute the limits, that is pi by 2 plus 6 into cos square theta into 1 by 2 pi, 0 to pi by 2 cos square theta is 1 by 2 pi by 2 plus cos power 4, 3 by 4, 1 by 2 pi by 2. So I can take that pi by 2 common, 4 and 4 comes out, a power 4 into pi by 2 comes out, and this will be 1, pi by 2 is 1, plus if pi by 2 comes out, and it will be 2 goes in 6 goes 3 times, plus if pi by this will be 3 by 8. This is 3 plus 1 is 4. 8 fours 32. 32 plus 3 35. 35 pi a power 4, 8 into 2 is 16. So this is the line integral of, yeah, this is the line integral what we have to find out for this function. But that line integral value, if you evaluate the double integration, you will get very easily. So this gives the uh, Green's theorem, and in my next lecture, I will discuss the Stokes theorem. We have three theorems. Green's theorem already I covered just now. Stokes theorem and Gauss divergence theorem. There are another two theorems. For divergence theorem, volume integral is required. So I will give, after the Stokes theorem, I will give some idea on finding the volume integral, and then I will move to the other theorem. Okay, prepare well.